Let's watch this scene from the movie Superman from 1978 and then let's analyze it with our superpowers of physics. Now the question we want to answer is, what is the deceleration that Lois Lane suffers when she is rescued by Superman? So she's falling at a constant acceleration, which is gravity, and then suddenly she stops because of Superman. What is that acceleration that Superman gives her to bring her to a stop? Okay, let's do some physics. So we have that Lois Lane is free falling from an initial height y sub-0 and is falling downwards, and Superman is going to meet her. We will get this as the y-axis, the vertical 1, 0 will be down here at the ground and all height is going to be positive. And if we want to calculate the acceleration that she is having when Superman reaches her, first of all we need to know what's the velocity that she has right here. So we're going to use the kinematics equations that we have learned so far. So for this linear motion free fall with constant acceleration, we have the following equation, where y0 is initial position, initial height, initial vertical velocity, and acceleration, which we know which is minus 9.8 meters per second squared. So let's put those numbers here. So initially c is addressed, and this is the acceleration which is going downwards, and because our positive axis is going upwards, then that has to be negative. Now we can calculate first of all what's the distance c has traveled. In order to know that, we need to know the time. That's why you have counted the time, and you know that it's about 7 seconds. So let's assume it's 7 seconds. And now let's substitute this 7 here. So y, that's what we are. So because we're interested in the distance, delta y is going to be negative 240 meters. Negative because the final position is smaller than the initial position, because it's going from a positive height to a smaller but also positive height. So well, that's delta y is negative 240 meters. With this, we can now calculate what is the velocity that she has right at that moment where she meets Superman. In order to do that, we use the relationship between velocity and acceleration in a linear motion with constant acceleration, which is given by this. And we substitute. We know that initial velocity is 0, we know that g is minus 9.8 meters per second squared, and we know that time is 7 seconds, so we only need to substitute here. So that is 68.6 meters per second. That's the velocity that she has when she meets Superman. But probably you're not familiar with meters per second so far, so let's try to transform that into something that you are more familiar, probably kilometers per hour or miles per hour. So let me just erase this. And now we just transform from seconds to hours and from meters to kilometers. "247 kilometers per hour. If you want to go to miles per hour, you only need to know that 1 mile is 1.609 kilometers, and you can do that yourself and find 153.5 miles per hour. So 153 miles per hour, that's her velocity when she meets Superman. But we will use 68.6, which is that's the SI units, that what we have to use when we are doing science. So V1 is the velocity that Lois Lane has when she reaches Superman's arms, and now, well, we know that her velocity, we know the distance that she has traveled. Now I want to calculate what is the acceleration due to just the deceleration, how she is going to reduce her initial this velocity. So by looking at this scene, we might guess if we get guess what is the distance that she travels or the time that she is decelerating. So if we want to calculate the acceleration, there are different ways to calculate that. We know that the acceleration is delta v divided by delta t. Delta v, final velocity, we know that is 0. So the initial velocity is this one. If we can guess what's the time that we see in that scene that this procedure takes, then we can calculate the acceleration. Another way of calculating the acceleration would be by guessing what's the distance that c is traveling. From that scene, my guess is that the time that I can see in that scene is, let's call it t2 to differentiate from the first time, which those 7 seconds. That time is about 1 second, and delta distance is about 1 meter. That's what roughly I can tell from that scene. So let's use these numbers to see what we get for the acceleration. In the first case, if time is equal to 1 second, I come here, a is equal to final velocity minus this velocity 1 divided by t2. Final velocity has to be 0 minus this velocity, sorry, this was negative because it was going down, so now minus, and minus it's plus 68.6 divided by 1, so we know this is 68.6 meters per second squared, and that is 7g. So that's 7 times the gravitational acceleration here on Earth, which is a lot. So it's not going to be a nice, smooth meeting with Superman. It's going to be a rough one. 7g is a lot of acceleration. But that's assuming that that's the time. But let's assume that what we see is that they spend about 1 meter to do that deceleration. What should be that deceleration then? Okay, we have this result. Let me just copy it here. Say that the first acceleration that we have found is 7g. Now let's see what will this assumption of delta y equal to 1 meter will give us. Now we are going to assume that the condition that we have is that c has traveled 1 meter in that deceleration process. So we know that delta y is going to be from here to here. So this is y initial and this is y final. So delta y, because the origin of coordinates is here, that's 0. It's positive upwards. Then we have final, which is smaller than initial. So this delta y is going to be minus 1 meter. Minus 1 meter. And we use the kinematics equations. We have this is going to be, so the same one that we use in the first case. This is velocity initial t plus 1/2 of at squared. And now this is the acceleration we are looking for. But here we have two unknowns. We don't know the time. We're assuming that this is for a deceleration through 1 meter, which is what we imposed here. But then we are looking for the acceleration, but we don't know the time. Well, we can use the relationship between velocity, acceleration, and time in a motion with constant acceleration. So we know that the final velocity is equal to the initial velocity plus the acceleration's time t. And we have these two equations, so we have a system of two equations with two unknowns, the acceleration and the time. We solve both of them, we find the time that she's traveling to see if that's 1 second or not. And more important, what we are looking for is the acceleration to see how high or how low that acceleration is. So what I'm going to do is I'm going to solve for acceleration here and then substitute here. These are the two equations that we have. From this expression, I have the v minus v1 divided by t, and we know that final velocity has to be 0, and we know that v1 was this negative 68.6. Remember, she was traveling downwards, so that's a negative velocity, and we found previously that the magnitude of that velocity is 68.6. So that is minus is going to be a positive. So that's the acceleration. I'm substituting that here. Delta y, sorry, that would be -1. V1 is this number here. And this is a positive, this is plus 1/2 of 68.6 times t squared. This square goes away with this time, and then I can simplify this expression. Let me do it up here. And that gives me 0.03 seconds, which is really slow. It doesn't agree with what we see. That what we see is that she is traveling about 1 meter and about 1 second. So that is telling us that in that scene they didn't reflect the fact that she was traveling at 68 meters per second. So that's the time. Now let's calculate the acceleration. We only need to substitute in the previous equation of the acceleration. And that is 233 g. That's a lot, and Lois Lane cannot survive to that. She would be dead. So this is just like an impact where she's going to go from 150 miles per hour to 0 in just 0.03. So that will kill her definitely. Now we know that Superman cannot do that, and it's just because of physics.